We will now only focus on supervised learning, and we will start with a very basic technique of supervised learning known as univariate linear regression. A univariate linear function, basically a straight line with input x and output y, has this form: y equals w1x plus w0. Say, for example, you have a data that looks like this. Basically, what you have is two columns. Your first column is house size, and your second column is dollar, the price of that house, right? And you have, let's say, quantity X, Y, A, B, C, D, and so on. So this is your data, a very simple data with only two columns, and what you would like to do is treat this house size as input and predict the price of the house. And this is how your data, when plotted, looks like. In x-axis we have the size of the house, and in y-axis we have the price of the house in $1,000. So as you can see, overall, as the size of the house increases, the price of the house also increases. For example, for this house that is 3,500 square feet, the price is also very high, $900,000, right? Now, univariate linear function is simply trying to learn the relationship between these two variables, these two columns, by using a straight line. We would like to fit a straight line into this data such that the data represents the pattern or the relationship between your input variable and your output variable. And such straight line relationship is represented by such an equation: W1x plus W0. What this equation simply means is, say for example, we have W1 equals 0.8 and W0 equals 0.6. Then what this model or what this equation simply tells you is your y will always be 0.8 times x plus 0.6. So say for example, if we figure out that these are the right weights of our univariate linear regression model, then if my input price of the house is, let's say, 10 square feet, then this will be 0.8 into 10 plus 0.6. That becomes your dollar price of the house. So the task here obviously is to find the correct values of W0 and W1, so that our model becomes really a good model. Our straight line becomes a line that represents as much of a strong relationship between these two variables. And these two variables, W0 and W1, are real valued coefficients that we would like to learn. And we use the letter W instead of, say, for example, when you are studying a straight line in mathematics, you usually read it at y equals to mx plus c, where you say m is the slope of the curve and c is the intercept, y-intercept. But here we see W1 and W0 as weights, and that's why we represent them using this signal, using this letter W. And these weights that we have to find out, W0, W1, all put together into a set of variables, becomes our weight function, our HWX, that we have to learn. So W1x plus W0, this is our this is our model or our function that we need to find out, learn. And x is a variable, and W0 and W1 are what we have to learn. Now this task of finding HW, basically your weight function, is called linear regression. And if our equation is in this format, where we have two W variables, and we would like to find the best values of W's, then this problem is simply linear regression. Basically, the question is, what should be my slope and intercept of the line that fits my data to minimize the empirical loss? When we say loss, what we mean is to maximize this correlation or relationship between your input variable and the output variable. So obviously, we need a mechanism in which we can calculate the loss or error. Say, for example, if my line is here, then I need a function or a technique that I can use to say this is a bad line. If I move the line slightly up here, there must be a mechanism that I can use to say this is a better line. And as the line gets closer to the black dotted line here, we should get a very a good signal that we are doing really good. And if we go further away, then we should get a signal that it's very bad. So how do we do that? This we do by using something. One example of doing that is using something known as a squared loss function. What we can simply do is with this with this initial loss function, with this initial univariate linear function that we have, our model, we initialize W0 and W1 to some really random value, and then calculate or make a prediction by using this equation, W0, W1 and W1, W0, and then you use it for your input, make a prediction. Then you subtract this from the actual output, actual dollar price. So let's say for 10 examples, you made these predictions, and then for these 10 examples, you also have the correct dollar price. Then we subtract them, square them, and then sum them. So this gives us a number that tells us how good or how bad our model is. If our model is really, really good, this will be something that's very, very close to Yj, our actual output labels, and the loss will be almost close to 0. If it is a really bad model, then the loss will be very high. So in this way, we can adjust W0 and W1, keep adjusting them until we get W0 and W1 such that we get a very small amount of loss. In other words, what we would like to do is find the minimum value or optimal value of W's, optimal values of our W vector, where the loss function, our loss HW, is minimum, right? So this is an optimization problem. Here's our equation for loss, right? This is what gives us loss. We can vary W1 and W0. And here the task is, what are the values of W1 and W0 that gives me the minimum loss? This is a minimization problem here. And we know from partial derivatives that in order to find the maximum or minimum value of an equation, we have to take partial derivatives. So if I take partial derivative of this equation and equate it to 0, that gives me the optimal values of W0 and W1 where loss is minimum. So this leaves me with these two equations where I can take the partial derivative of this equation with respect to W0 and partial derivative of the same equation with respect to W1. And this leaves me with two equations where I need to solve the partial derivative of these two equations. It turns out that because this equation does not have any nonlinearity in it, these two pairs of equations give us a unique solution to the values of W1 and W0. And these we can directly calculate by using these equations that we can derive from these two, by solving these two partial derivatives. In other words, if we say, for example, multiply our for each input data point, multiply x, y, sum x separately, sum y separately, sum the squares of x, and square the sum of x, and calculate this, we will get W1. Similarly, to get W0, you multiply W1 with the sum of all your inputs, and then subtract it from your output, and divide by n, you get W0, right? And you will get unique values like 0.323, 0.426. That gives you basically to your original straight line or your equation the slope and the y-intercept of your equation. So many forms of learning involve adjusting weights to minimize a loss. As we saw in the case of univariate linear regression, we saw that we have an equation like this where we want to adjust the weights to minimize our loss function, right? So it helps to have a mental picture of what's going on in weight space. So what is this weight space? So weight space is defined by all possible settings of weight. So you have your weights, maybe it ranges from 0 to 1, and this ranges also from 0 to 1. How do these weights affect the overall loss value? That's what we mean by visualizing the weight space, or trying to see that. Now, for the case of univariate linear regression, where we only have one variable as input and one variable as output, the weight space is defined by W0 and W1. And this weight space is two-dimensional. What we would like to do is see how this loss function, the values of this loss, change as we change W1 and W0. And this loss function turns out it's a convex function because we have no nonlinearity involved here. And this is how it looks. So here's our original part where we have housing area in x-axis and price in y-axis, and this is how our data points look like. And here's our weight space. What we have here is in x-axis all possible values of weight 0, maybe it ranges from 0 to 1. And in another axis, let's say if this is y-axis, we have weight 1. Once again, maybe this ranges from 0 to 1, right? Depending upon what range of W it is. And in the z-axis, the third axis, we have the loss. Now, as you can see, say for example, when your first weight W0 and your second weight W1 are both 0 at this point, you can see that the loss is very high, right? And then maybe at this point where you have weight 1, W1 as 1, and W2, W0 as still a 0, your loss is low but not extremely low, right? And probably there is a place somewhere here where this sort of surface is going down and becoming very less, or smallest value of loss, somewhere around this. And this is where you have around a specific point of where you have W0 and W1 and W0, and this is what gives you the best value of loss. In other words, if you randomly start, let's say, with W1 and W0 values over here, what you want to do is minimize or push the model, push the weights slowly towards this direction so that your loss becomes as less as possible, a smallest value possible for your problem. And it's very helpful to understand what's going on in this weight space as you change your weights, as you change your possible weights to minimize the loss. And almost all machine learning problems basically involve updating these weights until you get a very small amount of loss. And you will see that very frequently what we will observe is we will start with a very bad loss at the beginning, maybe somewhere around this corner like this, and then as the machine learning model learns, in other words, you may start from a line, something that looks like this with very bad values of W0 and W1, and slowly your model will learn as the loss decreases to push this line higher and higher so that it gets closer to the best optimal value. Your loss may not be 0, 100%, because you may not be able to fit all the data accurately, but what we want is to get the loss as less as possible. Next, we will extend the idea of univariate linear regression that we saw earlier to build models that are bigger or larger than linear models. In other words, we want to go beyond linear models, particularly for the regression problem. In this case, we may have multiple input columns, which we call multivariate regression problem. We may have non-linearity in our equation, which means that this may not be a simple equation. This may be a complex equation. And such equations defining minimum loss, where this your loss equation is complicated, non-linear, oftentimes involving many variables, like not just xj is a single variable, but many, it's a vector with a lot of values in it. Then such a minimum loss will have no closed form solution. What this means is when we decrease one variable in your weight matrix, say for example W0 or W1, your loss may behave unpredictably. Now, what we mean by unpredictably is this. For example, in case of two variables where you have W0 and W1, and then your loss is changing as W0 and W1 change, you see that as I decrease W1, let's say if this is 0 and this is 1 for this axis, as I increase W from 0 to some point, the loss keeps decreasing, right? And then at some point of W1, the loss is minimum, and then after that, the loss goes back again. In other words, there's like this concave structure of loss. It follows this concave pattern where concave or convex pattern where the minimum is at a place. So if you keep going in one direction, you will find the minimum loss. Now, when we may have loss functions which are so complicated that your loss may go down and then go back up and go down, go back up, go down, and that's when you know that even if you find a direction to go at the beginning, your direction may be wrong, or even if you find that you're going in the right direction, you may be stuck in something known as local minima. So this kind of behavior happens when your loss function is complicated. Now, such a problem where you have many variables that determine the loss, and the loss may not be predictable, is a general optimization problem. And we say that the problem is in a continuous weight space because these weight values are continuous. They are real continuous values. Now, such problems in algorithms can be addressed using algorithms such as hill climbing. We will not get into the details of what hill climbing algorithm is, but this is one of the algorithms that allows you to at least give you a solution when the problem is an optimization problem. In machine learning, however, we frequently use, or the basis for training for neural networks basically is an algorithm known as gradient descent. So this is the algorithm that is used for training almost all neural networks right now. And the idea behind this is we typically have a loss function that has very complex looking plot weight space like this. And what we want to do is find the best combination of optimal values of W1, W0, W0, W1. You may have more variables, W2, W3, and so on, so that your loss is minimum. Now let's look at how this gradient descent algorithm works. You start by randomly selecting W. So let's say if your W, this is a vector now. Let's say this is a set of W0, W1. So in case of univariate linear regression, we only have two variables, but in case of multivariate linear regression and more complex loss functions, we may have W2, W3, all the way up to Wn, right? So this is your weight vector. So we choose any point in the parameter space. In other words, we choose any point here, or you can say that we randomly initialize W0, W1, W2, all the way to Wn to some values, usually between 0 and 1. Now we loop until convergence. We will define what convergence means. We loop, for now we can imagine that we loop repeatedly many times, hundreds of times. We repeat, what do we repeat? For each Wi in W, that is for each your weight variable in your vector W, do this. Update your current W with the previous value of this W minus a constant alpha and your loss. So in other words, if I had, let's say, 0.5 as my initial W1, and this wasn't a very good weight, but let's say 0.7 was the best possible weight for this problem, then since this is not the best weight that you currently have, you will get some loss. Let's say the loss that comes out is 0.1, right? And then you multiply this loss with this constant alpha. And let's say if alpha is 0.01, then you multiply this, and whatever you get, you subtract from the existing W, which is 0.5, and then that becomes your new W, your new W naught. So in this way, what's happening here is this loss function tells you how bad your loss is from an ideal 0, let's say. And looking at how bad your current loss is, which implies how bad your current weight is, you use that, multiply that a factor, and you use that to update the current weight so that the weight becomes better each time. So you can imagine if I loop this for 100 times or 1,000 times, and if I repeat this, so this is the feedback signal, the loss function that tells you how bad your weights are currently. This is an iterative process where you continuously update the weight each time so that, like, the weights eventually converge or like settle down to good values. So when we say loop until convergence, we can say that until the weights don't change by a factor. Let's say if I see that for up to, let's say, 100 epochs, or let's say 100 rounds of this for loop, if I see that the weights don't change, there are no changes in any of the weights, then I can stop or choose many other ways in which we can stop the outer loop. But this is how weights are updated. Now this applies to almost any neural networks that we are going to discuss, or even the basic linear regression models or multivariate linear regression models. And this parameter, alpha, that we chose to multiply our loss is known as the learning rate. And it can be either be a fixed constant. Usually it is a small number like 0.001 or 0.01, etc. And or it can be something that decays over time. So initially it may be say 0.001, and then later it can be 0.0001 during the process of training. So it can be either a constant or it can decay over time. Now for univariate linear regression, this equation reduces to this. That's because we exactly know what the loss function is, and after calculating the derivative for W0 and W1, partial derivative, we will get this equation as we saw before. So this is our loss function given by this equation, and then we have W0 equals W0 plus alpha times your loss, and W1 is W1 plus alpha times your loss. We have a positive number here because usually the loss that you calculate is already negative, and that's what compensates for this plus sign. So far, we saw two techniques to calculate weights in case of a univariate linear regression. And here are the two techniques that we discussed so far. We saw that once we have our loss function that gives us our loss, we can obtain for each weights variable in our equation, loss equation, we can take the partial derivative of the loss function, set it to 0 to obtain the minimum loss. So this is the partial derivative with respect to W0, and this is with respect to W1. And in case of univariate linear regression, we saw that since we only have one variable as input and our loss function is quite easy to calculate, this can be solved into these two equations, and we can now we have a formula directly to calculate W0 and W1. We also saw a more general method to calculate weights, and this was using the gradient descent method. We discussed that the general equation to calculate loss is Wi is equals to Wi minus alpha times your derivative of the loss function. We also saw that in case of univariate linear regression, this sort of can be written as, or it can be expanded into two equations, where you have one equation to update W0 and another equation to update W1. The question is, what is the difference between these two methods, and which is more general? The answer is, this method is a more general method, and this is something that only applies to the case of univariate linear regression, and other linear models. That is because your calculation of partial derivative may not be always as easy. If you have a complex function here, that is, let's say, for example, a square, exponent, e to the power x, or some other more complicated nonlinear functions involved in your loss function, then calculating partial derivative, in other words, solving the partial derivative to come up with an equation like this, becomes extremely difficult, particularly when you have more than one input variable. Right now, xj is only one value, but if this becomes a vector with a lot of values in it, then coming up with equations like these becomes very challenging. Whereas this gives you a general way to calculate, as long as you have a way to calculate your loss function, then you can multiply that by alpha, subtract from W naught, and that gives you new values of W. So this is a much more general way of calculating or updating weights each time than the first way. Now this can also be very easily extended to calculate next weights. Let's say, for example, I have another weight W2. I can do W2 equals W2 plus alpha, and then sum of all items minus yj minus my output of the weight function xj. So times xj, this particular data point. So this gives me a sort of general equation that I can easily extend to calculate the weights of calculate the updated weight for any of the weight variable in my loss function.